Hi, and welcome to Lesson 7 in our unit on the nucleus. Here, as we move towards the end of this unit, we're really going to start to look at some very quirky things that nuclei do in specific circumstances. And the first of those is what we call nuclear fission. And so this is a diagram showing nuclear fission of a particular isotope, uranium-235. And you can see that the nucleus of uranium-235 is being split. And that's really what fission means. Fission just means splitting. So this is literally splitting this nucleus into two smaller nuclei and producing quite a bit of energy, as we'll discuss as we go in. So let's take a look. Fission just refers to exactly what we just discussed, right? It's the breaking of a large nucleus into a smaller nucleus. It's important to understand that only a few isotopes are fissionable. The triggering event for a fission is the absorption of a neutron by the fissioning nucleus, and that's going to cause that nucleus to split into two smaller isotopes. In this graph, you can see a list of the products that are produced through the fission of uranium-235. It's not always two of the same isotope. There's actually quite a few different isotopes that can be produced. This graph shows you the mass numbers of the typical isotopes that are produced, but you can see that it ranges quite a bit, even though there are more common isotopes produced than others. But notice also that when uranium-235 does this, that it produces additional neutrons. And so that's kind of interesting because the neutron is triggering this event, and this event is itself triggering more neutrons to be released. And so in the first part of the 20th century, it was discovered that if you take a bunch of these fissionable nuclei and you put them together in the same place and you start by fissioning one nucleus by absorbing a neutron, that's going to trigger the release of additional neutrons, which could be absorbed by surrounding nuclei and cause them to undergo fission and trigger the release of more neutrons, and so on and so forth. This becomes an exponential process, what's called a chain reaction. And so if we consider that just a few of the isotopes that we're aware of can undergo fission, only a few of those can actually undergo this chain reaction process. But of those, if you get a few billion of them and you put them together and you just start the fission party by throwing a neutron at one of them, my question to you is, what do you think is going to happen? Any thoughts? Well, this is what's going to happen. This is what the atomic bombs that were used at the end of World War II did. They started a chain reaction in uranium-235 nuclei, and then they just let it go. And the amount of energy that was produced through that process was more than anyone had ever seen to that point in human history. Without getting too much into the fine details of weapon design, the way that a fission bomb typically works is that we take two smaller masses of what's called enriched uranium, uranium that's been treated so that there's a lot of the fissionable uranium-235 in the sample, and you combine those two subcritical masses into a critical mass, which is enough so that the uncontrolled fission reaction can occur, and within instants, you then have a nuclear explosion. So this is the design of the little boy weapon, which was the first weapon that was used at the end of World War II. And you can see that there was two amounts of uranium-235 that were brought together through the action of a conventional explosive. And once they were brought together, fission occurred, and that was how the weapon worked. The fission bombs that were used to end World War II produced about 1,000 times as much energy as a ton of dynamite. So if you could imagine a ton of TNT and sort of lighting a match and getting out of there and the amount of energy that'd be released, fission weapons typically produce somewhere around 1,000 times as much, what's called a kiloton of energy. So a tremendous amount of energy from a very small package. So an obvious question is, well, where does all of that energy come from? And so in order to get your head around this, you have to understand that some of those laws of conservation that we've talked about in previous units do not apply at the level of nuclear chemistry. So conservation of energy and conservation of mass are always going to work in this course, except in these particular cases. During any nuclear reaction, a small amount of mass is converted into energy. And it's converted into energy according to a particularly famous equation from this gentleman down at the bottom, right, which is E equals mc squared. This is actually called the mass defect, because if you take all of the mass that you have before the fission reaction and you look at all the mass that you have afterwards, a tiny little bit of it is seemingly lost. It's not actually lost, it's just been converted into energy directly according to the mathematics in this equation. Let's look at what this equation means. So C is the speed of light, which is approximately 3.0 times 10 to the 8th meters per second. This is a very large number. It's in fact so large that we don't think anything can actually travel faster than this number in the universe. So it's a giant number. And so what that really means is that just a tiny amount of mass can be converted into a huge amount of energy. Here I'm using the famous metric unit known as the crap ton, right? It's just a ton of energy. The way that I've heard it explained is that the fission of one uranium-235 nucleus actually produces enough energy that you could move a grain of sand using that energy, which probably seems like, okay, who cares? Tiny thing, moving a tiny thing. But if we were to scale that up, that's like throwing a football at the moon and knocking the moon out of orbit. It's a tremendous amount of energy from a very, very small source. So when you do that with enough of them, you produce the kinds of energy that you see in nuclear weapons. Just to get a handle on how much energy we're talking about here, if you converted 1 gram of mass into energy, it would produce approximately 90 times 10 to the 12th joules of energy, which is roughly equivalent to either of the atomic weapons that were used to end World War II, which is why, of course, we like to use that term crap ton, right? It's just a crazy amount of energy that is produced through nuclear reactions. So if we go back and we think about how those nuclear weapons worked, you needed what was called enriched uranium. And what that means is that you've taken the sample of uranium and you've done things to it so that you've increased the proportion of fissionable nuclei in the sample. There's a few different isotopes of uranium. We saw uranium-238 previously when we did some alpha decay and some half-life. That is not the uranium that can undergo the chain reaction kinds of fission, but it is the most common type of uranium. The uranium that can undergo fission is uranium-235, which is 0.72% of all of the uranium atoms on Earth. You need to take your uranium samples that you get out of the ground, and you need to treat them in such a way so that you can increase the amount of uranium-235 in that sample. Nuclear weapons need uranium that's 90%, approximately 90%, uranium-235. By comparison, nuclear power only needs uranium that's 3% uranium-235. The way that uranium is enriched usually these days is in gas centrifuges. You can see a bunch of gas centrifuges on this slide, and you can see that they're made out of these aluminum tubes. And so if you pay attention to geopolitical intrigue, when it's thought that a country might be pursuing nuclear weapons development illegally, a lot of times the shipment of aluminum tubes is monitored because of their role in enriching uranium. Let's move away from weapons and let's talk about a beneficial use of nuclear energy, which of course is nuclear power. The way that nuclear power works is that it uses the heat that's produced through nuclear fission to generate electricity. In the core of the nuclear power plant, that's where your rods of uranium are. Those are what are called the fuel rods. And these rods produce a tremendous amount of heat. That heat is used to turn water into steam, and that steam is then pumped to turn turbines. And for reasons that will be made clear when you take physics, when you spin a turbine, which is a magnet inside of a coil of wire, that produces the alternating electrical current that we all use in our lives. So nuclear power plants aren't all that different from coal power plants or natural gas power plants or oil power plants. It's just that instead of burning the coal or burning the natural gas or burning the oil, here it's the heat that's produced through nuclear fission. And one of the benefits of this, of course, is that it produces no greenhouse gas waste. It just produces a lot of heat waste, which is the function of those big cooling towers that you've seen on Simpson-esque power plants, right? Those giant towers, those are just venting out the steam that's produced in order to cool things down. There's a couple of different important parts of a nuclear power plant that you should be aware of. So one is that in the core, not only do you have the fuel rods, but you also have control rods. And so these control rods work to absorb some of the neutrons that are produced, and this prolongs the chain reaction. You can make the chain reaction happen over a much longer period of time by absorbing some of the neutrons and controlling the overall amount of fission. Another thing that's really important is coolant. That keeps things from getting too hot. The fission reaction is going to produce a tremendous amount of heat, and so this coolant is going to be used in order to keep things from getting so hot that they would melt. And generally, you'd use something like water for that. At least in United States nuclear power plants, the coolant is often water. And finally, the other part that we'll point out is what's called the moderator. And so the moderator actually slows neutrons down. When neutrons are produced in fission reactions, they go incredibly fast, and most of them would actually be lost from the system. And so you need this moderator to slow down the neutrons and make it much more likely that they'll interact with other uranium nuclei and keep the fission reaction going. So here's a really important thing that I want you to remember. Probably the most important thing for you to remember as a scientifically literate citizen of the world. And that is that a nuclear power plant cannot explode like a nuclear weapon. It just cannot happen. And so you might be asking why not? And of course, it has to do with the enrichment. The nuclear material is nowhere near enriched enough to undergo the kinds of uncontrolled fission reactions needed for a nuclear weapon type explosion. So that's really good, right? I mean, that's a relief, but don't get too relieved. There are still quite a few problems with nuclear power, and so let's talk about those. So the first is that the nuclear material becomes depleted over time and it's still radioactive, so you have radioactive waste. All of that coolant that's been in contact with the fuel rods directly is radioactive, so that's more waste. The control rods are waste. Anything that was in that core becomes radioactive, and that has to be stored someplace. This map is actually showing you all of the locations in the country where nuclear waste is currently stored. It's currently just stored at the nuclear power plant itself, or at the facility that generates the waste. There's no centralized place to put it. There have been proposals to centralize it all in a specialized storage facility inside of a mountain in Nevada called Yucca Mountain, but obviously the citizens of Nevada aren't so keen upon being the nation's nuclear waste dump. So the storage of nuclear waste material has not really been figured out in the long term, and remember that these kinds of nuclear products have half-lives of many, 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 many years. In the case of uranium, it could be as long as 4.5 billion years, so you have to have some place to put it all where it's not going to get disturbed for very, very long time frames. The other thing that we can talk about is the condition known as a meltdown. So yeah, I mean, a nuclear power plant will not explode like a nuclear weapon, but it can undergo what's known as a meltdown. And that happens if the control rods and coolant systems stop functioning. If that occurs, the heat that's produced causes the uranium fuel material to get so hot that it can actually melt through the containment vessel. We actually cannot create a containment vessel that's secure enough to deal with this issue. And we have had a couple of meltdowns since nuclear power started being used by humanity. In Pennsylvania, there was one in the late 70s at 3 Mile Island, where a small amount of radioactive material was released into the environment. Not a tremendous amount, not something that's even measurable, but still a small amount was released. More recently, there was a meltdown in Japan at the Fukushima nuclear power plant, and that was because a tidal wave that was generated as a result of a massive earthquake caused the cooling systems to be shut down at the power plant long enough that there was an eventual meltdown and there was a release of nuclear material into the environment. This is probably going to wind up being one of the most expensive environmental cleanups in human history when it's all said and done, and people are still not really clear on how they're going to approach cleaning up this environment because they've really never seen anything like this. Generally speaking, however, nuclear power has been very free of human error, or at the very least there have been redundancies built into the system that have caught the problems and kept them from getting out of hand. There is, of course, one glaring exception, which is the Chernobyl nuclear power plant disaster. And so this wasn't actually a meltdown, really. What happened here was that a human error caused an explosion and led to the exposure of the core and spreading nuclear radiation and nuclear isotopes throughout the local environment and actually throughout the entire world, as those nuclear isotopes went up into the global circulation systems and were then precipitated out through normal precipitation action. The immediate area surrounding the Chernobyl plant was the city of Pripyat in Ukraine, and that entire city had to be evacuated and has never been re-inhabited. You can go there if you want to. If you wear protective clothing, you won't be exposed to enough radiation that it will be problematic. However, nobody can live there, except, of course, for the wildlife that has re-inhabited the environment that the humans have left behind. So this is a good reminder that when things go wrong with nuclear power plants, they can go so wrong that they result in the abandonment of cities. But fortunately for us, that is not something that has happened very often at all in the history of nuclear power. Thanks so much for watching this discussion of fission and how we use fission in nuclear weapons and, of course, in nuclear power. Make sure that you can do the following things here at the end. Make sure that you can identify a fission reaction and explain what happens during it. Make sure that you can explain how fission reactions can lead to nuclear explosions. Make sure that you can describe how nuclear power plants can function. and also make sure that you can explain the benefits and the problems associated with nuclear power. If you can do all of those things, you're doing great. If not, that's okay too. Take a moment and write down any questions that you have. You can always leave the questions below the video in the comments, or you can always get in touch with me through the information in the info field. Thanks again for watching. I really appreciate it. Have a great day.